Hello, a very good afternoon to all, and welcome to my class. Today, as we see in the screen, we are going to start a new chapter that is organic compound containing halogen, right? So, in today class, we are going to discuss about the alkyl halide, aryl halide, right? Halogens in a detailed way and try to solve some PYQ questions related to this chapter as well, right? So, this is what we are going to do today, right? So, this is the plan for our today class. So I hope my voice is audible to all of you and my screen is also visible. If you face any difficulty related to this, please let me know so that we can rectify this problem. Right? I hope all is good. Right? Okay. Yeah. So let's start with the today class. That is, in first some slides, we are going to see the preparation of alkyl halide, that how should we prepare alkyl halide, right? So we can prepare alkyl halide from alcohols. This is one of the best method for preparing alcohol because, in this method, when we treat the alcohol with the thionyl chloride, that is SOCl2, this will gives us the alkyl halide, and this one of the best method for the preparation of alkyl halide, right? So from alcohol, how will you prepare alcohol? When we treat alcohol with the pH3 or HX, right, then we'll get RH. Similarly, when we treat alcohol with concentrated HBr, then also we'll get this thing. And when we treat ROH with PCl3 and PCl5, then also we'll get this. So this is nothing but PCl3, right? Similarly, when we treat like when we have a CH3, CH2, and OH, and when we treat this with PCl5, right? PCl5, then also we'll get the CH3, CH2, and Cl, right? And the similar basis, we have a POCl3 and we have a SCl. Similar when we treat CH3, CH2, OH with PCl3, right? With the PCl3, then we'll get like CH3, CH2, Cl plus S3PO3. So this is the method by which you'll get the alkyl halide. Okay. Now the one of the best method here is when you treat CH3, CH2, and OH, right? With SOCl2. With the SOCl2, you will get CH3, CH2, and Cl plus byproduct as SO2 plus SCl. So both are gases, so they are easily removed, right? So this is one of the best method known as Darjan process, right? So this is one of the best method for the preparation of alkyl halide from the alcohol because in this SO2 and HCl is produced, which is in a vapor phase. So HCl, SO2 also present in a gaseous form, so it can be easily removed, and HCl is also present here in a vapor phase. So it can also be separated out from the alkyl halide, right? So out of these three methods, this last one, that is the Darjan process, this one is the most important method for the preparation of alkyl halide. So I hope this is clear to you. How will you prepare alkyl halide from alcohol? Okay. The next is that is the halogenation of the hydrocarbon. So by this also you can prepare this by the halogenation of hydrocarbon. For example, let's say we have a CH4, and if you do the halogenation Cl2 in presence of sunlight, then we'll have a product property of like we'll get CH3 Cl plus SCl. But the limitation of this reaction is this cannot be stopped at the one level. They further react with the they further react with the Cl2, and again CH2 Cl2 will be formed. Again SCl will be removed. Again, this will react to give us CaCl3, and in the next step, it will give CCl4. So, till all hydrogen are consumed, the product will get, right? So, if you want to obtain only this level up to CH3Cl, then Cl2 must be taken in the, CH4 taken in the excess and Cl2 taken in the minimum. So this is the basic properties of this. How will you prepare from the hydrocarbons? Yeah, similar for the bromine. So we can also prepare bromine like this. But there is an exception in case of iodine. So we cannot prepare iodine by this method, right? Why we not prepare iodine by this method? Because in iodine, if you treat CH4 with I2 in presence of sunlight, what they'll form? They will form CH3I and plus HI. So due to formation of this HI, this reaction become reversible. So this reaction become reversible. Why this become reversible? So this become reversible due to formation of reversible due to formation of HI. So due to formation of HI, this reaction become reversible, right? So due to the formation of HI, this reaction become reversible, and we have to add an oxidizing agent. So we have to add an oxidizing, right? We have to add an oxidizing agent, right? Just wait for a minute. I'll just connect charges. Okay, so due to formation of HI, this reaction become reversible. So what we have to do, we have to add an oxidizing agent, right? So we have to add an oxidizing agent like HiO3. Okay, like HiO3. So this oxidizing agent, what they do, when the HiO3 react with the HiO3 react with HI, and they will convert this into H2O plus I2. Now this HI formation will be, disturbed, and we get the product like H2 and I2. So the problem is sorted, right? So whenever we treat CH4 with I2, the formation of HI, and due to this the reaction become reversible. So what to do to overcome this difficulty? So we have to add an oxidizing agent like HiO3, because HI is a very good reducing agent. So what we have to do, we have to add an oxidizing agent like HiO3. When you add oxidizing agent like HiO3, they will convert HI into H2 and I2. Thus the problem resolved. Yeah. So just remember here, halogenation of hydrocarbon, halogenation of methane, chlorination will be possible. Bromination will also possible, but iodination possible with this exception. So we have to add an oxidizing agent. Similarly, fluorination can't be possible because fluorine form very explosive when they react with the CH4 to form CH3F. This reaction become very explosive. So this reaction is also not possible, right? So always remember these three things from the halogenation of hydrocarbon. Now, these are the side chain halogenation of alkyl benzene, right? So let's see side chain halogenation of alkyl benzene. Right. So how will you say that the side chain halogenation of alkyl benzene? So this is the toluene we say, and when they treated with X2 in the presence of sunlight, it will form CH3X. So benzyl halide. Similarly, this will treated to X2, it will form benzyl halide. And right. So this will also a benzoin trihalide. Similar, just like a CH, 3 Cl, CH2, Cl2, and CHCl3 and CCl4, we get the product like this one. Right. Now, this one is also very important. That is the addition of hydrogen halide to alkenes. So this one is going to be very, 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 very important. That is what is the addition of hydrogen halide to alkenes, right? So let us assume we have a alkene like CH3, CH, double bond CH2, right? So let us assume we have alkene like propene. And if we add HBr to it, now we add HBr to it. This is called hydrogen halide, right? Now, this is partial negative charge, this is partial positive charge, right? So according to Marconi's rule, the negative part goes to those carbon atom which contain the lesser number of hydrogen atom, or we say negative part goes to this carbon and this will goes to this carbon. So the product form is CH3, CH2, CH2, and this is what? No. CH3, CH, here Br will come, na? Okay, so there Br will become, and here again H will come. So the product become CH3, or we can write as CH3, CH, right? CH3, CH, and this will be Br, right? CH3, CHBr, and CH3. So we'll get the product like this, like a 2-bromopropane. So this is known as Marconi's rule. So this is known as Marconi's rule, right? Similarly, when we treat this CH3, CH plus CH2 with HBr in presence of some peroxide, that is known as anti-Marconic rule. Anti-Marconic rule, or we say peroxide effect. Peroxide effect, right? So CH3, CH double bond, CH2, HBr, they react with my anti-Marconic or peroxide effect. So what they form? They will form. Here the negative part goes to those carbon which contain the more number. So this will goes to this, right? So the product is CH3, CH2, CH2, and this is nothing but Br. So this is one bromopropane. So in the Marconic rule, we get two bromopropane. That is two bromopropane, right? But in case of this, we'll get one bromopropane. So we'll get only one bromopropane. So always remember this thing, right? What happened when you treat with the peroxide and the Marconic rule. So this is the addition of hydrogen halide to the alkenes. So this is how we can add hydrogen halide to alkenes. So by two way, either Marconic rule or either anti-Marconic rule. Whenever you add Marconic rule, you get the secondary, that is the 2-bromopropane. And whenever you add anti-Marconic or peroxide effect, you get the 1-bromopropane, right? So this is all. I hope this is clear to you. Yeah, good. Very good. Now, the next one is addition of halogen to alkene, both alkynes, right? So this is the addition of halogen. So let us assume this is a alkene. We have alkene. Now we add halogen to this alkene, right? So we have a alkene. Now we add halogen to this alkene. So we get CXCX. This is called vicinal dihalide. So when the two halogen atoms are present on the two adjacent carbon atom, then this is known as a vicinal dihalide. Similarly, in the alkynes, when you add this, you'll also get the vicinal dihalide, right? So someone asked what is vicinal dihalide. So you can say when the two halogen atoms are adjacent to the each carbon, then they are known as the vicinal dihalide, right? Now, here we can also discuss this thing in a detailed way. That is reaction with the phosphorus halide. So basically, haloalkanes are conventionally prepared by the reaction of alcohol with the phosphorus halide like PCl3, PCl5 or PBr3 according to the following equation. So this is the complete equation here. When the 3C2H3 mole of ethanol is treated to PCl3, we'll get the 3C2H5Cl plus S3PO3. Similarly, when there's PCl5, we get the POCl3 plus. And when they are treated with PBr3, we'll get the 3C2H5Br and S3P, right? So this is the product we get. Now, reaction with the thionyl chloride. So basically, the thionyl chloride, that is SOCl2, is the another reagent which react with an alcohol to will chloroalkane. As both the byproduct, that is SO2 and HCl, are gases, the purification of the final product is not required. So this is one of the best method for the preparation of alkyl halide, because in this there is no need for the purification, right? Okay. Now, how will you prepare haloarenes? So the preparation of haloarenes is done, and that is we prepare by the alcohol, by the hydrocarbons, or by the alkene, right? So this is the three methods that we use to prepare the alkyl halide. Now, how will you prepare haloarene? So basically from the aromatic hydrocarbon, that is haloarenes are obtained by direct halogenation of the aromatic hydrocarbon in presence of a catalyst. Usually iron filling or iron halide is used as the catalyst. So here what we use as a catalyst, iron fillings or iron halide basically used as the catalyst. So we can say that this is the benzene, and when the benzene is undergo direct halogenation, that is with X2 in presence of Fe, or we say FeCl3, will get halobenzene, or we say haloarene, right? Where X may be Cl and Br. Here also iodine is not prepared due to the reversible nature, and fluorination cannot be occur due to reaction is very explosive. The direct hydrogenation of the aromatic hydrocarbon is not useful reaction, since the HI produced reduce the aryl halide back to the aromatic hydrocarbon. We already discussed this thing, I guess. right? So we have to add an oxidizing agent to overcome this, right? So here we can also say when the benzene is treated with I2, they will form hydrobenzene plus HI. Now this reaction is reversible. So however, in the presence of an oxidizing agent such as nitric acid, iodic acid, right, and mercuric oxide. So this is known as iodic acid. So HiO3 and the mercuric oxide. The HI produced is either oxidized to iodine or is assimilated as the mercury iodide, and thus the iodobenzene is obtained. So this is the reaction when the 5HI is treated with the HiO3, the 3I2 and 3I2 will be formed. Right. So 3I2 and 3H2 will be formed. So this is about the iodination. Now, from the diazonium salt. So this is one of the best method. By this method, you can also prepare the fluorobenzene, which cannot be prepared by the simple halogenation of the aromatic compounds, right? So from diazonium salt. So BDC salt, or we say benzene diazonium salt, is formed by treating an aromatic primary amine with NaNO, right? So the benzene diazonium salt is formed BDC is formed by the benzene diazonium salt is formed by treating an aromatic primary amine with the NaNO2 and dilute HCl at the low temperature. This process is also known as the diazonation. We are going to study this thing in a amine chapters, right? So when the aniline, this is nothing but aniline, right? This is known as aniline. Just remember this thing. Aniline. Okay. So when the aniline is treated with NaNO2 plus dilute HCl, right? So when the aniline is treated with NaNO2 plus dilute HCl at 273 to 278 Kelvin, very cold condition, then the formation of BDC will be takes place, right? Then the BDC will be formed as we known as benzene disonium chloride, right? This is BDC, benzene disonium chloride. Now, diazonium salts are highly reactive compound and therefore they are used in the preparation of large number of arene derivatives. So remember this, diazonium salts are very reactive compound, right? These are the very reactive compound and thus they are used in the preparation of large number of arene derivatives. Whenever a diazonium salt is treated with the copper chloride, that is CO2Cl2, or copper bromide like CO2Br2, the corresponding haloarene is formed, right? So whenever the diazonium salt is treated with copper 1 chloride, this is Cu2Cl2 copper, right? And a copper one that is CO2Br2, then corresponding haloarene are formed. If we treat this BDC with the Cu2Cl2, here I'll show you. If you treat with this Cu2 and Cl2, you will get the chlorobenzene, right? And similarly, if you treat with the Cu2 Br2, you will get bromobenzene. Right? You will get the bromobenzene. So the corresponding haloarene is formed, right? So this reaction is known as Sandmeyer reaction and it is used for introducing a chloro or bromo group in the benzene ring, right? So this reaction is known as a Sandmeyer reaction and it is used for introducing a chloro or a bromo group in the benzene ring, right? So just remember this thing. It is known as a Sandmeyer reaction, right? Good. Now, here we can also show that we can prepare four things by this way our own BDC. So when you treat BDC with the copper chloride FCl, you'll get a chlorobenzene, right? Plus N2. So when you treat BDC with the CuHCl, you'll get chlorobenzene plus N2. Similarly, when you treat BDC with the CuBr you'll get a bromobenzene plus N2 plus Cl negative. Similarly, when you treat BDC with the Ki, you'll get the iodobenzene, right? And last but not the least, this one is the most important, also known as a Blass-Sachs reaction. Right. So also known as the Blass-Sachs reaction. So this is the method for the preparation of fluorobenzene because fluorobenzene cannot be prepared by the simple aromatization or we say by the simple aromatic hydrocarbon. So this can be prepared by this special method when the BDC is treated with the NaNO2 and HBF4 in the presence of 272 to 278 Kelvin. So this is how we can prepare the fluorobenzene. So always remember this flow chart when the BDC is treated with the copper Cl chloride a copper chloride and HCl, so we'll get the chlorobenzene. And similarly, when they are treated with the copper bromide HBr, we'll get the bromobenzene. And this reaction is known as Sandmeyer reaction. Right. So this reaction is also known as Sandmeyer reaction. Right. So I hope this is clear to you. Good. Now, haloarenes. Okay. Haloarenes can also be prepared by reacting benzene diazonium chloride with a copper powder in presence of corresponding halogen acid. This reaction is called Gutterman reaction. So what is the difference between the Gutterman and the Sandmeyer? So in Sandmeyer, we use the reagent like copper chloride and HCl, right? When treated copper chloride, HCl, copper bromide and HBr. But in this, we'll treat Gutterman, we'll treat only copper with HCl and copper with HBr. So this halogen can also be prepared by reacting BDC with the copper powder in presence of corresponding halogen acid, and this reaction is called Gutterman reaction, which is shown below. Right. So this is called the Gutterman reaction. Always remember this thing, Gutterman. Okay, so this is known as Gutterman reaction. Now, what are the properties of the haloalkanes and halogens? So if now I'm talking about the chemical properties because we already done with the we already done with the physical properties. So now let's study with the properties of the haloalkanes and chemical properties. So basically the nature of the CX bond in a alkyl halide, that is the carbon halogen bond is formed by the overlap of the sp3 hybrid orbital of carbon atom with the p orbital of the halogen atom, right? So the nature of CX bond in alkyl halide, the carbon halogen bond is formed by the overlap of the sp3 hybrid orbital of the carbon atom with the p orbital of the halogen atom. As we can see that in sp3 orbital we have one empty orbital of this. So as one of the move from fluorine to iodine, the size of the halogen atom increases and hence the overlapping decreases, right? Because the when you move from the fluorine to iodine, the size of is increases, and due to this, this will be increases. Just wait for a 2 minutes, guys. Just read this for 5 minutes. Just give me 5 minutes, right? I'll be back. Right. So, sorry for the delay. Right. Now start with the class. So the nature of CX bond in alkyl halide, that is the carbon halogen bond, is formed by the overlap of the sp3 hybrid orbital of the carbon atom with the p orbital of the halogen orbital, right? So sp3 hybrid orbital of the carbon and the p orbital of the halogen atom. So by overlapping of this, the bond will be formed. Now, as one moves from fluorine to iodine, definitely size increases because we know that fluorine is first member of this group and iodine is the last member of the group. So definitely when you move from fluorine to iodine, the size start increasing, right? Hence the overlap decrease. As the size increasing, the overlap tendency become decrease. So hence CX bond become longer and weaker on going from alkyl fluoride to alkyl iodide. So in case if I'm asking whether chloromethane and and the iodomethane, which bond is the more reactive? So we can say that the bond which break easily are more reactive. So as the size of the iodine is much as compared to the chlorine, the overlapping is less. So if the less overlapping is there, then the bond is weaker, and this is why they are more reactive. Or this we can say that the iodomethane bond break more easily as compared to chloromethane. Also, the halogen are more electronegative than carbon. Thus, their electron density along the CX bond is displaced in the direction of the halogen. We all know that because halogen is more electron dense, more electronegative, so they take away the electron. They shift the electron towards itself. Thus, the CX bond in the polar in nature. Now, the carbon atom bears a partial positive charge, and halogen atom bears a partial negative charge. So, this is what happening. So this polar CX bond, right? So this is polarity is induced. So someone asked how polarity is introduced between the carbon and halogen bond. So you can say that we know that halogen is the electron withdrawing group. Halogen is a good electronegative element. So they tends to shift the electron towards itself. So direction of the halogen, right? The CX bond in polar in nature. Because due to this, the carbon acquires the partial positive charge and the halogen require partial negative charge. Right? Okay. Now, what are the physical properties of this, basically the alkyl halide and aryl halide? So let's discuss some physical properties. So the lower alkyl halide like CH3F, CH3Cl, CH3Br, CH3I, or we say C2H5Cl are gaseous at room temperature, right? So the lower alkyl halide like fluoromethane, chloromethane, bromomethane, or we say chloroethane. So they are gases at room temperature, and the other alkyl halide containing up to C18 are liquid having a high boiling point, right? So haloalkanes and haloarenes are moderatively polar molecule, right? But still they are immiscible in water. So this is very important thing that sometimes the questions were coming from this. Why alkyl halide being polar, but still why they are insoluble in water? Why they are immiscible with water? So it is basically due to their inability to form hydrogen bond with the water molecule. So it will be not able to form hydrogen bond with the water molecule. Now the melting and boiling points of haloalkanes and haloarenes are higher than those of their parent hydrocarbon. So as if I'm comparing with the hydrocarbon, their melting and boiling points are high as compared to the hydrocarbons, right? Why? Because the greater molecular mass and hence greater magnitude of the van der Waals force, because we know that the van der Waals force comes into picture when the molecular mass is more. So if the two compounds having more molecular mass, then definitely van der Waals force acting according to it. Now, the second one is the existence of intermolecular dipole-dipole interaction as shown below. So in this, the dipole-dipole interaction is also possible between the halogen atom. So these are the boiling points of haloalkanes and haloarine. So now if I'm comparing the boiling points of fluorochlorobromine with the hydrocarbon. So this is in the first we have a hydrocarbon, right? So we have a hydrocarbon like XH bond. So in case of CS3X, we have a C2H5X, we have a C6H5X. So if I'm considering about the chloromethane, chloroethane, and the chlorobenzene, or we say aryl halide. So we have energy like this, that is the XH having 1115. Similarly, in this 184, and this it will become 351. So we can say that boiling point increases, right? Gradually they will increases. Similarly, when you move from this to this, then also we have a seen increase in the boiling points, right? So these are the boiling points of haloalkane and haloarine. Now, all monohalobenzenes are liquid at room temperature. So this point is also very important. All monohalobenzenes are liquid at room temperature. So all monohalogen benzene. Monohalogen means either I'm talking about the chlorobenzene, fluorobenzene, iodobenzene. So all monohalobenzenes are liquid at the room temperature. Among dichlorobenzene, the para isomer have the highest melting point. So why para isomer have the highest melting point, beta? It is due to the greater symmetry and that cause a better packing of the molecule in the para isomer. So always remember this, among the dihalobenzene, the para isomer have the highest melting point and it is due to the greater symmetry that cause a better packing of a molecule in the para isomer, right? Like we have a Cl and Cl. So we have this is orthochlorobenzene, this is a metachlorobenzene, and this is a parachlorobenzene. So as we observe that the parachlorobenzene having the melting point of 325 Kelvin, where the metachlorobenzene having the melting point of 249. Similarly, orthochlorobenzene has a melting point of 256 Kelvin. Right. So this is all about the melting point of the following, right? Whether it is a ortho, meta, or para. Now, chemical properties like halo compounds can undergo the following types of reactions. So which type of reaction generally halo compounds undergo, beta? So halo compounds undergo four types of reaction mainly. The first one is substitution reaction. The second one is elimination reaction. The third one is reaction of metal. And the fourth one is the reduction. So basically halo compounds undergo four types of chemical reaction. Either it will be the substitution, elimination, reaction with the metals and reduction. So these four types of reaction they generally go. Right. Now, substitution. So what is the substitution reaction? So basically substitution reaction are those in which the atom or group of atom from the reactant molecule is displaced by the another atom or a group of the atom. For example, on treating chloroethane with the sodium hydroxide, right, the chlorine atom of the chloroethane is substituted by the hydroxyl group and ethanol is formed as the reaction product, right? Here we can see that here the chlorine is become more negative. They wants to take the electron and they release this C2H5. Now this OH negative ion attaches to the C2H5 and the formation will take place. So this is known as substitution reaction, right? When treating chlorobenzene with the sodium hydroxide is an example of this substitution reaction. Basically what is happening here, chlorine atom of the chloroethane is substituted by the hydroxyl group and the hydroxyl group and ethanol is formed as the reaction product. Now, in this reaction, it is to be noted that the hydroxide ion acts as a nucleophile because it displaces the chlorine atom from the C2H5Cl as chloride ion and another nucleophile, right? So in this reaction, it is noted that the hydroxyl ion, that is a nucleophile, displaces the chlorine atom from C2H5Cl chloride ion, which is another nucleophile, means nucleophile displaces nucleophile. Such reaction which are initiated by the attack of a nucleophile are known as nucleophilic reaction or we say nucleophilic substitution reaction. So basically in haloalkane, the carbon atom carrying the halogen atom is electron deficient due to minus I effect of the halogen atom. So this electron deficient carbon atom is susceptible to attack by a nucleophile, right? So this electron deficient carbon atom is susceptible to attack by a nucleophile. Thus, you may conclude that the haloalkanes Thus, you may conclude that the haloalkanes undergo nucleophilic substitution reaction. So, following are a few examples of the nucleophilic substitution reaction of the haloalkane. That is how how this undergo nucleophilic substitution reaction. Similarly, when you treat haloalkane, that is Rx with the OH, NH3, CN, SH, RNS2 over or RCC negative, this will be formed. Similarly, what form? Basically, let me write with an example. For example, when you treat CH3, CH2, and Cl with OH, that is, it either be NaOH or anything base, it will be. So what will form, that is NaCl will be removed and this OL will be formed. So they will get alcohol, right? So this alkyl halide is converted into alcohol. Similarly, when they are treated with NH3, it will form NH2. When treated with CN, they will form RCN. Now here important note here, when this CH3, right? When this CH3 is treated with, uh, just wait for a minute. Just right. So we can see that like CH3, CH2, which we have. Mm, yeah. So when you treat CH3, CH2, Cl, and when we react with KCl, right? So when you react this CH3, CH2, Cl with KCl, what you'll get? You'll get like nothing but CH3, CH2, and this is Cl, right? So this is CH3, CH2, and Cl, right? So when the CH3, CH2, Cl react with KCl, we'll get CH3, CH2, and Cl, right? And KCl, you get as a byproduct. Now, on the similar basis, if you have CH3, CH2, and Cl, and now when you treat with AgCl, then what you will get? You will get CH3, CH2, and NC. So this point you must remember. Why this is happening here? Because if I'm talking about the KCN, KCN being ionic bond, so what KCN does, KCN break dissociate this K plus and Cn negative, right? And Cn negative. So we know that C and N having triple bond and having negative charge to this carbon atom. So here nitrogen also having two lone pair of electron, carbon also having two lone pair of electrons. So either will they can donate electron. But we know that the more electronegative element cannot donate the lone pair of electron easily. So in this case, carbon can donate their electrons. So we'll get the Cn in this KCl, right? But if I'm talking about the AgCN, AgCN bond is not purely covalent. So we'll not purely ionic. So we'll only have a lone pair of electron in nitrogen because carbon having four electrons and therefore engage in the bond formation. So carbon having no lone pair of electrons, the only possibility here is nitrogen should donate their electron. So they will make CH3 and C. So always remember, whenever alkyl halide is treated with the AgCN, they will form isocyanide. When they are treated with the KCN, due to ionic nature of KCN, they will form cyanide. So this point you must remember, right? Good. So in all the above reaction, the stronger nucleophile like OH negative, C2H5O negative, CN or NH3 displays a weaker nucleophile like X negative, right? So in all this, this will be happening takes place in the above reaction. The stronger nucleophile like HO negative, C2H5O negative, CN negative or NH3, they all can display the weaker nucleophile S negative, right? So these are the stronger nucleophile and they are the weaker nucleophile. Okay, good. Now, what is the mechanism of the nucleophilic substitution reaction? So if you're talking about the mechanism of the nucleophilic substitution reaction, we can observe this thing. The nucleophilic substitution reaction could be either SN1 or SN2 type. Right, SN1 means nucleophilic substitution 1 and SN2 means nucleophilic substitution order 2. So when the nucleophilic attack the haloalkane and simultaneously the leaving group leaves, then the reaction is called nucleophilic substitution bimolecular, or we say SN2. So in this, both these things are taking place at the same time. Right. So both these things are taking place at the same time when the nucleophile attack the haloalkane and simultaneously the living group leaves then the reaction is called nucleophilic substitution bimolecular, or we say SN2 reaction. So in SN2 reaction we have a transition state where we'll have a carbon show plus plus five, plus five valency as well. So how this so? Because basically here we can say that this is a CH3, 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 Cl. So Cl having more electron active than carbon, so they want to take away of the electron and try to break the bond in this fashion. On the similar way, OH is attacking from the back side, right? So this is called a transition state. So transition takes place. Now this will Cl will be removed and this OH will be acting opposite to this, right? So also note that it is in a one-step process and the transition state involve two species, right? Transition state involve two species. The formation of this transition state is the rate determining step in this the mechanism. Hence, here the bond making and the bond breaking takes place simultaneously, right? So here the bond making and the bond making and bond breaking takes place simultaneously. Now the nucleophile OH attacks from one side of the carbon atom, whereas the leaving group Cl leaves from the opposite direction. Hence, there is an inversion of the configuration and the carbon atom. So we can say that in SN2 we got the inversion. How will you get the inversion? Because we can see now, we can see very clearly the nucleophile OH attack from one side of the carbon atom, whereas the leaving group Cl leave from the opposite direction. So here there is an inversion configuration of the carbon atom. Now, primary alkyl halide undergo substitution by SN2 mechanism. Why? Because we know that in primary alkyl halide we have only one bulky alkyl group. So if the more number of bulky group increase, then the back donation of back nucleophilic back attack is not possible. Due to high repulsion they will be provided if the larger group are present. So that's why primary alkyl undergo substitution by the SN2 mechanism. However, in case of a tertiary alkyl halide, the substitution takes place by an alternative mechanism, that is a substitution nucleophilic unimolecular or SNO mechanism. For example, in the hydrolysis of 2-bromo-2-methylpropane, any one molecule participate in the rate determining step, which is the dissociation of the alkyl halide to alkyl cation and the bromide. Thus, alkyl cation is a carbocation and formation is slow and rate determining step. Right? So after this, as soon as this carbocation is formed, the nucleophile, which is a water solvent molecule, attack on it and which is a fast step. So in this, the formation of carbocation is the slowest step and rate determining step. Similar on the SN2, the formation of transition state is the rate determining step, or it is the slowest step. Right. Finally, the alkyl ammonium ion loses a proton to give the alcohol as the product. So we'll get this. So since the SN1 reaction proceed via the formation of carbocation, the stability of the carbocation formed in an important factor in the SN1 reaction. So what is the stability of the carbocation? So we know that primary carbocation is less stable as compared to the tertiary, because in tertiary we have a 3,3 donor group. So let us consider the following carbocations like primary, secondary, and tertiary. Right? So tertiary is one of the most stable. So this will most stable due to presence of 3,3 donor group. Now, haloarenes are almost unreactive to reagents such as NaOH, C2H5ONA, and NaCN and NH3 under the ordinary condition, but can show nucleophilic substitution reaction under some drastic condition, that is a high pressure and temperature. Right. So haloarenes are almost unreactive to a reagent such as NaOH, C2H5ONA, NaCN, and NH3 under the ordinary laboratory condition, but can show nucleophilic substitution reaction under a very drastic condition. Like when the chlorobenzene is treated with 6 to 8% of NaOH or 623 Kelvin or 300 atm, in presence of dilute HCl, we get the phenol. Now, it is also observed that the presence of electron withdrawing group, such as the NO2 group, at ortho and para position, but not at the meta position, with respect to the halogen, activate the halogen towards the nucleophilic displacement. Right. So it is important note here when the NO2 group or any electron withdrawing group is attached to the ortho para directing group, not at the meta position, with respect to the halogen, activate the halogen towards the nucleophilic displacement reaction. Now, here we can observe this. This 4-nitrochlorobenzene, when treated with NaOH at 453 Kelvin, they will form phenol and 4-nitrophenol. So haloarenes can also readily undergo substitution reaction in benzene ring. The benzene ring is an electron rich species, therefore it is attacked by an electron deficient species such as NO2. So as the ortho and para position in haloarenes are electron rich due to resonance, right? The electrophile substitution takes place mainly at these position. For example, the nitration of the chlorobenzene with the mixture of concentrated HNO3 and H2SO4 give a mixture of a 2-nitrochlorobenzene and 4-nitrochlorobenzene. Here we can say that this is a chlorobenzene. When they are treated with a concentrated HNO3, nitration will take place in ortho and para because a Cl is the electron donating due to the R effect, resonance effect. They will donate the lone pair of electron. So they will ortho and para substitute. So they will give ortho and para, that is 2-nitrochlorobenzene and 4-nitrochlorobenzene. So this is what we get. Now, CX bond energy value. So here bond is CF and having bond energy 485. Similarly, CCl having bond energy 339. Similar CBr having the bond energy 284 and the CI having the bond energy of 213, having very minimum bond energy. So these bond energy values show that the CI bond is a weaker bond and CF bond is the strongest bond. Therefore, the order of reactivity of a haloalkene in iodoalkane is like iodoalkane is more because due to the larger size and easily break. So comparing the haloalkanes and haloarenes, the haloalkanes are found to be more reactive. So this question is also very important. Out of haloalkene and haloarene, which one is found to be more reactive and why? So always remember this. Haloalkane are found to be more reactive than haloarene in a reaction involving the breaking of CX bond, where X is FCl, Why? So it is due to the existence of phenomenon of resonance which cause carbon halogen bond to acquire double bond character in the haloarene and thus resonating structure of the chlorobenzene, as we can show that. So, right, this will acquire the double bond character. So due to presence of this double bond, wait. Yeah, so due to this presence of a double bond, this double bond here, I'm talking about this. So due to presence of this double bond, this bond become strong and difficult to break. So we can say that this is a chlorobenzene is what? That is chlorobenzene. They have more reactive or less reactive. So chlorobenzene is less reactive if you compare them with the alkyl halide, right? Now, so now we are going to see some elimination reaction. So just give me 2 minutes, then we are going to start our new, that is a elimination reaction, right? Right. So what is the elimination reaction? So basically, when haloalkanes are heated with the aqueous solution of potassium or sodium hydroxide, when the haloalkanes are heated with the aqueous solution of potassium or sodium hydroxide, the major product formed is the alcohol produced by the nucleophilic displacement of halogen atom by HO negative, right? So when you treat this when we treat chloroethane with the aqueous KOH, we'll get only alcohol plus Cl. We already know this. This is a nucleophilic substitution reaction they will undergo. So we already know about this reaction, right? Now, if the haloalkanes is heated with the concentrated alcoholic potassium hydroxide, here important note here, concentrated alcoholic, right? So concentrated alcoholic potassium hydroxide, the major product formed is alkene due to the elimination of hydrogen halide. And this is also known as beta elimination, or we say dehydrohalogenation reaction. So let's understand this reaction. Let us assume, suppose you have a CH3, CH, Cl, CH2, and CH2. So let us assume you have a chloro alkyl light like this, that is a 2-chloro, and this is nothing but butane. Now, when you treat with KOH, so there is a two possibility, KOH alcoholic there, right? So there is two possibility. This KCl will be removed, and elimination will also takes place with OH, and here they want to accept one H from this. So which position they are accepting H? For example, the halogen atom attached to this carbon, so this carbon being alpha carbon. Now next carbon next to the alpha carbon is called beta carbon. So this is either this side or this side. So this will be lead to the beta carbon, right? So this is alpha carbon, this is beta carbon, right? Now, if you remove electron from this beta, so it will form CH2 double bond CH, CH2, right, and CH3. So one possibility is this, and the another possibility, if we do remove, if we remove from this, so this will form CH double bond CH, and this is CH3. Observe very carefully. So here we have a two donor group to this alkene group. Here we have only one donor. So which one is more stable? Obviously this one is. So this is in major product. So this is called major product. And this is called, right. So one is called major product and another is called minor product, right? So this thing is given by the Sirjeff rule, known as Sirjeff rule. So according to the Sirjeff rule, major product is given by those having the symmetricity between the two double bond atom, right? And this one is given by the minor product. So if the structure of the alkyl halide in such a way that it can undergo elimination in the two different way, then more highly substituted alkene. So this having the more highly substituted alkene having two donating group CH3. So the more highly substituted alkene, that is having the lesser number of hydrogen atom on the doubly bonded carbon atom, is the major product. Here we can say that lesser number of hydrogen atom. Right, so they will form the major product by the elimination, and this is known as Sirjeff rule. For example, elimination reaction of two bromobutane give two butene as the major product according to the Sirjeff rule. Right, so we can say that this will form in the 80%. This is the similar expression for the previous one. Right, so this will form 80%. So this will form the 20. Right, so this is all about the Sirjeff rule. Now, this thing is very, very important. That is the reaction with the metal. So in the reaction with the metal, the first scientist that generally come into the picture is known as Grignard. Right? They are basically a French chemist, right? So reaction with the metal, that is the haloalkanes and haloarine react with the variety of metal like zinc, magnesium, and lithium. And the compounds so obtained have a metal atom directly bonded to a carbon atom. Such compound in which the metal atom is directly bonded to a carbon atom are known as organometallic compound. Always remember, such compound in which the metal atom is directly bonded to a carbon atom. When the metal atom is directly bonded to a carbon atom, then such compounds are called organometallic compounds. The organometallic compound of magnesium with alkyl and halide are known as Grignard region. Right. Similarly, the organometallic compound of magnesium with alkyl and halide are known as Grignard region, right? Okay. So here we can say that we have a C2H5Cl plus Mg. So we have a C2H5 MgCl, that is RMgH. So these are named after the French chemist, right? So these are named after the French chemist Victor Grignard. Okay, so Victor Grignard was awarded in the Nobel Prize in 1912 and he introduced organomagnesium halide as a common synthetic reagent. Okay, now, so alkyl halide react with the metallic sodium in presence of dry ether to form symmetrical higher alkane, right? So basically what happening here now, alkyl halide react with the metallic sodium in presence of a dry ether to form a symmetrical higher alkane, and this reaction is known as Wolff's reaction. So this reaction is generally used when you have to convert two, that is when you convert propene into hexane or we say ethane into butane. So always when the number is double, whenever you want to convert the want to prepare the double number of carbon atom then that you have. So by using this formula, you can convert this. So this is known as Wolff's reaction. So basically the ethyl bromide can react with the lead in presence of dry ether to form tetraethyl lead, which is used as an anti-knocking agent in a gasoline used for the running automobile. So this is a bromomethane. This react with the 4 Pb, so it will form tetraethyl lead. Right, tetraethyl and lead. Now, when the haloalkanes react with the alkyl halide in presence of sodium and dry ether. So, when haloarenes react with the alkyl halide in presence of sodium and other alkyl derivative of the benzene or form, this reaction is called Wurtz-Fittig reaction. Now, similarly, the formation of diphenyl is also taking place when the two chlorobenzene is react together. For example, when the two chlorobenzene, right? So here we can say that this 2-chloro will be removed. Then what you'll get? That is, we'll get the diphenyl. Right? So this is what we get, that is diphenyl. Now, the next or last method of the alkyl halide is reduction. So haloalkane can be reduced to the corresponding alkane. For example, bromoethane can be reduced to ethane by using a metal catalyst such as a nickel, palladium, or platinum, or by using a hydrochloric acid HI in presence of the red phosphorus. So this is what we have bromoethane. When they are treated with the nickel or platinum, it will form ethane. Right. Similarly, when the idomethane is treated with this will form ethanol. Okay. Now, what is the distinction between haloalkanes and haloarenes? So, haloalkanes and haloarenes can be distinguished by silver nitrate AgNO3 test, and haloarenes react with AgNO3, give white precipitate of AgCl, while the haloarenes do not react. Right? Now, so I hope this is clear to you. Till so far, all points are clear. Anyone having any kind of doubt, you can ask Twitter. Right. Good. So now some useful polyhalogen compounds. So let me wait. This should be visible to you, right? No, perfectly fine. Okay, so there are some useful polyhalogen compounds that we have. So what are the some useful polyhalogen compound we have, beta? A large number of polyhalogen aliphatic and aromatic halogen compounds are known. So these are extensively used as a solvent, pesticides, antacids, or some of the important compounds are chloroform, iodoform, and carbon tetrachloride, benzene hexachloride, DD. So these are some important compounds of the polyhalogen compound like chloroform, iodoform, carbon tetrachloride, benzene hexachloride, VSC, and the DDT. Now let us now study some of these compounds. So what is chloroform, beta? So chloroform is the derivative of the simplest hydrocarbon, methane, and its IUPAC name is trichloromethane. So we know that methane, what is methane? So this is methane, right? That is CH4. So this is the simplest hydrocarbon of methane, which is derivative. So we can derive this as CH and Cl3. So this will become the chloroform. ठीक है, or we known as trichloromethane. So how will you prepare this? So we can prepare from ethanol. So chloroform is prepared in the laboratory by treating ethanol or propanol with the chlorine gas in the presence of an alkali. So whenever you treat ethanol, right, ethanol or propanol with the chlorine gas. So ethanol, and we have a chlorine gas, so we'll form ethanol. Now, when this ethanol is still heated, they remove this 3Cl2 and formation of trichloroethanol. That is also known as chloral will take place. Similarly, calcium hydroxide react with the CCl3, right? CCl3, CHO, and they will form calcium formate and the chloroform. So by this, they will form calcium formate and the chloroform. So this is how you can actually prepare chloroform, right? Now, on the similar basis, you can also prepare from the propanol, like how when the propanol is treated with the 3Cl2 in presence of HCl, the formation of like Cl3C, COCS3. Now again, when this treated with the calcium hydroxide, the calcium acetate and chloroform. So this is the two way by which you can prepare chloroform. So chloroform we can prepare from the ethanol. Now, chloroform is a colorless, sweet-smelling liquid having boiling point of 354 Kelvin. It is slowly oxidized by air in presence of light to poisonous gas, ozone. This one is very, very important, ozone gas. Yeah. So this one is very, very important. Chloroform is a colorless, sweet-smelling liquid boiling point of 354 Kelvin, and it is slowly oxidized by air in presence of light to poisonous gas. Phosgene. Chemically, phosgene is a carbonyl chloride that is COCA2, right? Therefore, the chloroform is stored in the dark colored bottle. So, how to avoid this difficulty? So, the chloroform will be stored in the dark bottle. So, dark bottle, right? To produce to protect it from the light. The bottle are completely filled so that the air is kept out. A small amount of ethanol is added to chloroform to convert toxic phosgene if formed into the non-toxic compound that is ethyl carbonate, right? So this point is very, very, very important. That is, the chloroform is a colorless, sweet-smelling liquid having boiling point 334 Kelvin, and it is slowly oxidized by the air in presence of light to a poisonous gas called ozone gas. Chemically, ozone gas is, carbonyl chloride, that is COCl2. Therefore, the chloroform is stored in the dark color bottle to protect it from the light. Now, the bottle are completely filled so that the air is kept out, and the small amount of ethanol is added to chloroform to convert toxic frozen gas if it form into a non-toxic compound, or we say ethyl carbonate, right? Now, chloroform is used in the isocyanide test for the detection of primary amine. In this test, a mixture of amine and chloroform is heated with alcoholic NaOH a fall spelling isocyanide is obtained. This test is also known as a carbolamine test. So always remember this is carbolamine test. So this test will give me only the primary amine. So only primary amine can give this test known as a carbolamine test. So it can be used to test the aliphatic or aromatic primary amine. Now what is iodoform beta? So iodoform is a pale yellow sad, iodoform. Iodoform is a pale yellow solid with a distinct smell. Its IUPAC name is a triiodomethane. And the preparation, how will you prepare iodoform? So iodoform is prepared by the heating ethanol or acetone with iodine in presence of alkali. So we'll treat when ethanol is treated with the NaOH, we'll get the iodoform, right? Now, similarly, when the CS3CO, CS3I2, 4NaOH, acetone is treated, we'll get the iodoform as well. So from ethanol and from acetone, we can prepare by both way iodoform. Now, yellow crystal of iodoform can easily be recognized by the characteristic smell formation of iodoform. It used to test the compounds containing CH3CO or CH3CHOH group. This test is known as iodoform test, and iodoform is used as an antiseptic. So this one is also very, very important. Now, what are the structure of dichloro diphenyl trichloroethane? So this is the full form of the DDT, that is a diphenyl trichloroethane, right? So it is available in the several different form like a powder or aerosol form or granules, etc. So DDT will be present in the many way. So this is the structure of the DDT, that is we have a chloro and CH3Cl3. That's why their name is known dichloro. So we have a two chlorine group, dichloro and phenyl, and we have a at number one we have a trichloroethane, right? Trichloroethane. So what is the uses? So it is used mainly to control mosquito borne malaria. So it is used mainly to control the mosquito or borne malaria. It is also used in agriculture insecticides. The use of DDT has been banned in many countries because being non-biodegradable, it accumulates in the environment and is toxic to the other living organisms such as mammal, birds, and fishes. Right. So this is some method for the preparation of this. That is how should we prepare this, right? So this is RH. Similarly, when we treat RH, this is a halogenation. So when you treat RH with the Cl2 in presence of sunlight, we get this, right? So we'll get the structure like this. Okay. Now, similarly, when you treat ROH with the SCl, NaCl2, or we say PCl3 or PCl5 or SOCl2, out of the SOCl2 is the best method, then we also get RCl. Similarly, when you treat ROH plus Cl2, FeFeCl3 or CO2Cl2, then we also get this, right? Now, with the aqueous KOH, it will give ROH. Similarly, magnesium and dry ether, it will give RMgCl. Na, they will form RR, also known as Roots reaction, and lead with same, and the dry ether, and the Na dry ether, and nickel, platinum, or palladium, alkyl phosphorus. Now, these are the PYQ questions of this chapter. So, Ki in acetone undergo SN2 reaction with each PQRNS, the type of reaction they have. Okay, so we all know that the bulky group cause steric hindrance. So right, bulky group SN, we have a SN2 reaction. So for SN2, we know the order. What is the order for the SN2 reaction, beta? We know that for the SN2, since the bulky group is more, so attack is from backside is not possible in case of bulky group. So attack is from one. So what is the order in SN2? That is 1 degree, 2 degree, and 3 degree. Right. So this order you must remember. Now, the bulky atom cause steric hindrance in the formation of the transition state. Therefore, the higher homologous Q are less reactive than the lower homologous P. Right. So you have to identify this. So which one of the following is more reactive? So more reactive, like the option is B. That is S, then P, then R, or then right. So S, P, and R and Q. Right. So in compound as the transition state is highly stabilized. So this is how you can actually arrange this. Now, this is the statement based question. So what the question asks, beta beta, actually they are asking Bromobenzene upon reacting with Br2F2 it give 1,4-dibromobenzene as the major product. So this is absolutely correct because we know that whenever the bromobenzene is yeah. So bromobenzene upon reaction. Wait. Yeah. Right. So bromobenzene upon heating with Br2 and F2. So what you will get this influence of some iron fillings, right? So you'll get because we know that this is an ortho-para directing group. So you'll get one Br and here also we have a Br. So this will you'll get 1,4-dibromobenzene. So this is absolutely correct. Statement second state that in bromobenzene, the inductive effect of the bromo group is more dominant than the mesomeric effect in directing the incoming electrophile. So in bromobenzene, the inductive effect of the bromo, no, inductive effect is if the inductive effect is dominated, then they wants to tends to increase this electron towards itself, and the meta product substituted will take place. So in the bromobenzene, the inductive effect of the bromo group is not much more dominant than the mesomeric effect in directing in the incoming electrophile. Right. So statement one is true, but statement two is false. Now, how will you remember this question? What is this? So basically, which of the following compound does not react by the SN1 mechanism? So you have to identify which of the following compound will not be react by the SN1 mechanism. So out of the following, which compound will not react by the SN1 mechanism? Anyone wants to tell the answer? Anyone? Right. So in this question, they're generally asking which of the following compound does not react by the SN1 mechanism. Right. So basically, SN1 mechanism means what beta? The reaction will not be able to proceed by SN2 SN2 they are asking or SN1. So they're asking about the SN1 mechanism. As there is a bulky group attached to it, it's alpha carbon. Hence the reaction will proceed by SN1 mechanism. So we can say we can understood this thing because in this we have a SN1 for SN1 what you need? You need 3 degree, 2 degree, and 1. Right. So here due to presence of this bulky group, this won't go SN1 reaction. So the correct option is C. Right, that is C1. This one. Which of the following compound does not react with the SN1 mechanism? So this will not react with the SN1 mechanism. This will be react with the SN2 mechanism. Now, there are, we can say that there are four solvent A1, A2, A3, and N4. The dielectric constant for the solvent are in the order A2 and A1 having same and A4 say having greater than A1. Among them, only A2 and A3 are capable of forming hydrogen bond. Which of the solvent will be most suitable for SN1 reaction? So they are asking which of the solvent is more suitable for the SN1. For SN1 reaction, they are favored by the increase in the polarity of the solvent. So higher the polarity of the solvent, higher is the rate of SN1 reaction. So which one is the correct? That is B2. That is A2. So if the value of A2 is more, if the value of A2 is more, then this product will be formed. Right. Now, again, this equation that is consider this equation. Consider the following reaction when the methyl and bromide, methyl, bromide, methyl, bromide. What is the correct order of the SN1 reaction? So for SN1, we know this is 3, 2, and 1. So out of this, which will be the 1 degree? This will be the least one, and this will be the second degree, right? And this will be the again double bond we have. So for the fourth one, what is the correct order? That is C. So maximum will be C, B, and A. So C having more, and then compared to B, and then for A. So this is how we can actually calculate this, right? So ease of nucleophilic substitution among the following compound upon the treatment with aqueous NaOH. So you have to identify ease of substitution in which the substitution will take place much more easily as compared to the any other one, right? So no simple funda is there. Most is the aliphatic character, right? So ease of the nucleophile substitution of the following product will get removed across NaOH. So this is the correct answer is fourth. That is fourth one. That is CH2Cl. Then the second one then the third one, and that is the fourth one. So, right. Right. So this one is the fourth, second, third, and first. So this is all about the important question related to this chapter. So we already cover all the questions, important question related to this chapter and all, right? And we also cover an entire topic. So just revise this thing. This will going to be very important for you all. Right, just remember this thing all. What is this iodoform? What is this reaction? What is addition? What is the reaction of this? Right. So if you remember this all this thing, this chart, this block diagram, then you can easily remember the equation and you can able to solve a question related to this chapter. Right. So this is the big role here. How will you remember this all this thing? If you know this thing, then you can easily solve the question related to this. Right. I hope no doubt in this. All things are very much clear, right? So anyone having any kind of doubt, you can ask. No, yeah. So this is all for today class. In next class, we are going to discuss organic compound with containing oxygen family. That is alcohol, phenol, and ether. We are going to discuss, right? So this is for today all, and in the next class, we are going to discuss the next organic compounds chapter, right? Till revise this thing so that you can able to solve the question related to this, right?